Roman concrete. The Romans built structures from concrete over 2,000 years ago that still stand today. The Pantheon in Rome, completed in 128 AD, has the world's largest unreinforced concrete dome. It's been standing for nearly 1,100 years, with no structural repairs needed to the dome itself. Roman harbors built from concrete withstand ocean waves after 2 millennia. The harbor at Caesarea, built around 15 BCE, has concrete piers still intact after 2,000 years of constant wave action. Modern concrete, by comparison, begins deteriorating within decades. Highway overpasses built in the 1960s are crumbling and need replacement. Concrete structures have typical lifespans of 50–100 years before requiring major repairs. Our concrete is far weaker and less durable than Roman concrete, despite having modern chemistry, engineering, and quality control. The difference is the formula. Roman concrete used a specific mixture of volcanic ash, lime, and seawater that created a chemical reaction producing extremely durable material. The concrete actually gets stronger over time as seawater interacts with the volcanic ash, creating crystalline structures that reinforce the material. This is the opposite of modern concrete, which weakens when exposed to salt water. Modern concrete uses Portland cement, a completely different formula developed in the 1800s. Portland cement is cheaper and faster to produce, sets more quickly, and became the global standard. But it's far less durable than Roman concrete. It weakens over time, particularly in seawater, where salt water corrodes the reinforcing steel and causes concrete to crack and crumble. We know the basic ingredients of Roman concrete: volcanic ash, pozzolana, lime, and aggregate. But knowing the ingredients isn't the same as knowing the precise formula, mixing ratios, and technique. Romans didn't leave detailed manufacturing instructions. The knowledge was passed from master craftsmen to apprentices and was eventually lost when the Roman Empire fell and large-scale construction projects ceased. Modern scientists have analyzed Roman concrete samples and attempted to recreate it. They've had some success producing concrete with similar properties, but replicating it exactly has proven difficult. The volcanic ash matters. Not just any volcanic ash, but specific types from specific Italian volcanoes. The mixing process matters. The order ingredients are combined, the water content, the mixing duration. The curing conditions matter. All these variables must be right, and we don't have the complete formula. Research published in 2017 showed that the key to Roman concrete's durability is a rare mineral called aluminum tobermorite, which forms through the interaction of seawater with the volcanic ash in the concrete. This mineral reinforces the concrete over time. Modern concrete doesn't produce this mineral, which is why it weakens rather than strengthens with age. Even when researchers create concrete similar to Roman concrete, it's not economically viable for widespread use. The ingredients are more expensive than Portland cement. The mixing and curing process takes longer. The construction industry has invested trillions in infrastructure based on Portland cement. Switching to a different formula, even a superior one, would require restructuring the entire concrete industry. So we continue building structures from concrete that will crumble within decades, knowing that the Romans built better concrete 2,000 years ago with primitive tools and no chemistry knowledge. We have the technical capability to analyze materials at the molecular level, but we can't replicate what illiterate laborers made routinely in ancient Rome. The irony is complete. Our advanced concrete is inferior to ancient concrete. Our infrastructure crumbles while Roman structures endure. We lost the knowledge of how to make better concrete and replaced it with worse concrete that profits from constant replacement and repair. Damascus Steel. Damascus Steel, produced primarily between 1100 and 1700 AD, created blades of legendary sharpness and durability. The steel had distinctive wavy patterns on the surface and could be sharpened to edges so fine they could cut through gun barrels and silk scarves with equal ease. Swords made from Damascus steel were prized throughout the medieval world for their quality. The steel was produced primarily in the Middle East and India, using techniques that were closely guarded secrets. The manufacturing process created steel with carbon nanotubes and carbide nanowires, structures that modern metallurgy has only recently begun to understand, giving the blades extraordinary properties. Damascus steel blades could be sharpened to angles impossible with ordinary steel without becoming brittle and breaking. They maintained sharp edges far longer than other swords. They were flexible enough to bend without breaking, but hard enough to cut through armor. These properties made them superior to any other blade technology of the time. Historical accounts describe Damascus steel blades cutting through gun barrels, iron or steel tubes that ordinary swords couldn't damage. Other accounts describe the blades cutting falling silk scarves, demonstrating sharpness so extreme that the blade's own weight was sufficient to slice through delicate fabric. The production of true Damascus steel stopped around 1750. The exact reason is unclear, possibly the loss of master smiths who knew the technique, possibly depletion of the specific ore needed, possibly both. Whatever the cause, the knowledge disappeared. Modern metallurgists have attempted to recreate Damascus steel for over a century. They've analyzed surviving blades at the microscopic level using electron microscopy, identifying the carbon nanotube structures that give the steel its properties. They understand what makes it work. But understanding the result isn't the same as knowing the process. Various smiths have created Damascus steel using pattern welding techniques, layering different types of steel to create similar visual patterns. But these modern reproductions don't have the same properties as historical Damascus steel. They look similar, but don't perform the same. The wavy pattern can be replicated, but the extraordinary sharpness, edge retention, and flexibility cannot. Recent research suggests the original process involved specific impurities in the ore, trace amounts of vanadium and other elements that created the carbide structures during forging. The ore used may have come from specific exhausted mines, making exact replication impossible even if we knew the complete technique. We have electron microscopes, spectroscopy, and materials science knowledge that would have seemed like magic to medieval smiths. Yet, we cannot make blades as good as theirs. The knowledge of how to forge Damascus steel died with the smiths who practiced it, and despite our advanced technology, we haven't fully recovered it. Stradivarius Violins. Antonio Stradivari made violins in Cremona, Italy, between 1680 and 1737. About 650 of his instruments survive today. They are considered the finest violins ever made, selling for millions of dollars and used by the world's top violinists. The sound quality of a Stradivarius violin has never been matched by modern instruments. Violin makers have tried for 300 years to replicate Stradivarius violins. They've analyzed every aspect: the wood, the varnish, the dimensions, the construction techniques. Modern makers build violins following Stradivari's patterns exactly, using similar wood, copying his methods as closely as possible. The instruments look nearly identical, but they don't sound the same. Blind tests consistently show that professional violinists can distinguish Stradivarius instruments from modern copies. The Stradivarius produces a richer, more complex tone that modern instruments cannot match. Multiple theories attempt to explain the superior sound. One suggests the wood Stradivari used came from trees that grew during the Maunder Minimum, a period of reduced solar activity from 1645 to 1715 that created colder temperatures and slower tree growth, producing denser wood with better acoustic properties. The same wood is no longer available because climate conditions have changed. Another theory focuses on the varnish. Stradivari's varnish formula was never recorded and has been lost. Chemical analysis of the varnish on surviving instruments shows complex mixtures of resins, but replicating the exact formula and application technique has proven impossible. The varnish affects how the wood vibrates, influencing sound quality. A third theory suggests wood treatment. Stradivari may have treated the wood with minerals or chemicals before construction, altering its acoustic properties. Some researchers claim to have found borax and other minerals in the wood, suggesting chemical treatment that modern makers don't replicate. Recent studies using CT scans and acoustic analysis have mapped Stradivarius violins in extraordinary detail. Scientists understand how the instruments produce sound, how the wood grain affects vibration, how the varnish influences tone. They can explain what makes the sound different, but explaining why it sounds better doesn't enable replicating it. Modern violin making has advanced enormously since the 1700s. Contemporary makers understand acoustics and materials science that Stradivari never knew. They use precision tools he didn't have, yet they cannot make instruments that sound as good as his. The knowledge of exactly how Stradivari achieved his results has been lost. Greek fire. Greek fire was an incendiary weapon used by the Byzantine Empire from the 7th century until the empire's fall in 1453. The weapon was devastatingly effective in naval battles. It burned on water, couldn't be extinguished with water, and stuck to targets like napalm. It gave the Byzantine navy a decisive advantage for centuries. Contemporary accounts describe Greek fire as a liquid projected through bronze tubes mounted on ships, igniting on contact with air or water. The flames were bright, produced thick smoke, and burned intensely enough to destroy enemy ships rapidly. Attempts to extinguish it with water only spread the flames. The formula for Greek fire was a closely guarded state secret. Only a few people knew how to manufacture it, and the knowledge was passed down through specific families who produced it for the Byzantine military. The extreme secrecy was intentional. The Byzantines understood that their naval superiority depended on enemies not acquiring the weapon. The weapon saved Constantinople from multiple sieges. In 678 AD, Greek fire destroyed the Arab fleet besieging Constantinople, forcing the Arabs to retreat. In 941 AD, it destroyed a Russian fleet of 1,000 ships. In each case, the weapon proved decisive. When Constantinople fell to the Ottomans in 1453, the knowledge of Greek fire was apparently lost. No complete formula survived. The families who manufactured it were killed, fled, or took the secret to their graves. What remained were historical descriptions of its effects, not instructions for making it. Modern historians and chemists have attempted to recreate Greek fire based on historical accounts. The leading theory is that it was based on petroleum or naphtha combined with resins, sulfur, and quicklime. The quicklime would react with water to generate heat, igniting the petroleum. This mixture would explain why it burned on water and couldn't be extinguished with water. But this is speculation based on effects, not on actual knowledge of the formula. Various proposed recreations produce incendiary mixtures that burn on water, but we can't verify if any of them match the original Greek fire. We don't know the exact ingredients, proportions, or preparation methods. The Byzantines used Greek fire for over 700 years. It was a proven, reliable military technology manufactured consistently across centuries. Then the knowledge vanished completely. We can make napalm and other incendiaries that are probably more effective than Greek fire, but we cannot make Greek fire itself because the formula was kept so secret that it was lost entirely when the last people who knew it died. The Saturn V Rocket. The Saturn V rocket launched humans to the moon between 1967 and 1973. It remains the most powerful rocket ever flown, capable of lifting 140 tons to low Earth orbit and sending 50 tons to the moon. It had a perfect operational record: 13 launches, 13 successes, including all Apollo moon missions. NASA officially retired the Saturn V in 1973 after the final Skylab launch. The rocket was expensive to operate, and the moon landing program had achieved its goal. The manufacturing infrastructure was dismantled, and the engineers who designed it moved to other projects or retired. Here's the problem: we cannot build another Saturn V rocket. The blueprints exist, archived in multiple locations, but blueprints aren't sufficient to manufacture complex systems. The Saturn V consisted of over 3 million parts made by thousands of contractors. Each part required specific manufacturing processes, tools, and techniques that weren't always documented in detail. The F1 engine that powered the Saturn V's first stage was an engineering marvel, the most powerful single-chamber rocket engine ever flown. 5 F1 engines generated 7.5 million pounds of thrust. The engines were built by Rocketdyne using techniques that included hand-welding critical components and adjustments made by experienced engineers based on feel and experience rather than written specifications. Much of this tacit knowledge, the know-how that experienced workers developed through practice, was never written down. When those workers retired or died, the knowledge went with them. The blueprints show what the parts should look like, but not exactly how to make them or assemble them. NASA attempted to recreate F-1 engines in the 2010s for potential use in future heavy-lift rockets. Engineers examined surviving engines in museums, reviewed archived documents, and tried to reverse engineer the designs. They found that some manufacturing techniques used in the 1960s are no longer practiced. Some materials are no longer available. Some tooling doesn't exist anymore. The companies that made many Saturn V components no longer exist. The manufacturing facilities were repurposed or demolished. The supply chains are gone. Even if we had complete knowledge of how to build every part, we'd have to recreate the entire industrial infrastructure from scratch. Modern rockets use different technologies, materials, and design philosophies. SpaceX's Falcon Heavy can lift comparable payloads using completely different engineering. NASA's Space Launch System uses modern engines and materials. These rockets don't recreate the Saturn V. They replace it with contemporary alternatives. But the fact remains, we put humans on the moon using a rocket we can no longer build. The knowledge of how to manufacture the Saturn V was lost not through catastrophe or secrecy, but through the mundane process of engineers retiring and facilities closing. Antikythera Mechanism. The Antikythera Mechanism is an ancient Greek analog computer discovered in a shipwreck in 1901. Dating to around 100 BCE, it's a complex bronze device with dozens of interlocking gears that calculated astronomical positions and predicted eclipses decades in advance. It's the most sophisticated mechanical device known from antiquity. The mechanism includes differential gearing, a technique not seen again in surviving artifacts until medieval astronomical clocks over 1,000 years later. The precision of the gears and the complexity of the calculations the device performed far exceed what historians thought ancient civilizations were capable of building. We know what the Antikythera mechanism did. Decades of research, X-ray analysis, and computer modeling have revealed its functions. It tracked the moon's phases, predicted eclipses, calculated the timing of the Olympic Games, and modeled the irregular orbit of the moon with remarkable accuracy. For its time, it was an extraordinarily sophisticated astronomical calculator. But we don't know exactly how it was made. The gears are cut with precision that seems impossible for ancient tools. The device required advanced knowledge of differential gearing, gear ratios, and mechanical computing. Who designed it? How was it manufactured? Was it unique, or were there others like it? No similar devices have been found. No ancient texts describe how to build such mechanisms. It appears in history as a fully developed, sophisticated device with no apparent predecessors and no known successors. The technology to create it seemingly appeared and disappeared without trace. Modern attempts to replicate the Antikythera mechanism can produce devices that function similarly, but we're using modern machine tools, precise measurements, and metallurgy knowledge the Greeks didn't have. Replicating it using only tools and techniques available in 100 BCE has proven extraordinarily difficult. The surviving mechanism is heavily corroded and incomplete. It was underwater for 2,000 years. Researchers estimate that about 30% of the original device survives. Reconstructing the complete design requires speculation. Multiple competing reconstructions exist, each making different assumptions about the missing parts. What's particularly frustrating is that this level of mechanical sophistication apparently existed in antiquity, was used for a specific purpose, then disappeared completely for over a millennium. The knowledge of how to design and build such mechanisms was lost, and when mechanical astronomy devices appeared again in medieval Europe, they had to be reinvented from scratch. We can make far more sophisticated computers now, but we cannot make the Antikythera mechanism the way it was originally made because the techniques used to create it have been lost to history. Medieval stained glass. Medieval cathedrals contain stained glass windows that produce colors that cannot be reproduced exactly with modern techniques. Particularly famous is cathedral blue, a specific deep blue color found in windows at Chartres Cathedral and other 12th-13th century churches. Modern glassmakers have attempted to recreate this color for over a century and cannot match it exactly. The same is true for certain reds, purples, and other colors found in medieval glass. The color in medieval stained glass comes from metal compounds added to molten glass: cobalt for blue, copper for green and red, manganese for purple. But achieving the exact hue, depth, and luminosity requires precise control of the glass composition, firing temperature, oxidation conditions during manufacturing, and cooling process. Medieval glassmakers achieved this through trial and error and carefully guarded techniques passed from master to apprentice over generations. When the techniques were lost, probably during the Renaissance when architectural styles changed and large stained glass windows became less common, the knowledge of how to produce these specific colors disappeared. The workshops that made medieval glass closed. The masters died without fully documenting their methods, and the tradition was broken. Modern analysis can identify the chemical composition of medieval glass using spectroscopy and other techniques. Scientists can see exactly what elements are present and in what proportions, but knowing what's in the glass doesn't reveal how to make it. The chemistry is only part of the process. Temperature curves during firing, cooling rates, atmospheric conditions in the kiln, and dozens of other variables all affect the final color. Attempts to recreate cathedral blue and other medieval glass colors have produced approximations that are close but not identical. The modern glass might have the same chemical composition, but subtle differences in manufacturing process create different colors. Experts examining medieval glass next to modern reproductions can distinguish them. The medieval glass has depth and luminosity that modern versions lack. Light passes through it differently, producing richer colors and more complex visual effects. Part of the problem is that medieval glass wasn't uniform. It contained impurities and variations, bubbles, streaks, thickness variations, that affected how light scattered through it. Modern glass manufacturing aims for consistency and purity, removing the defects that gave medieval glass its character. The imperfections weren't bugs. They were features that contributed to the overall visual effect. Making glass that matches medieval quality requires intentionally introducing controlled imperfections in just the right ways. Difficult to do consistently. Another factor is the raw materials. Medieval glassmakers used materials from specific sources, particular types of sand, metal oxides from specific ores, wood ash from specific trees for flux. These exact materials may no longer be available. The sand from medieval quarries was used up centuries ago. The ores from medieval mines are depleted. The forests providing wood ash for flux are a different species than medieval forests. Modern substitutes produce similar but not identical results. The firing process also matters. Medieval glass was fired in wood-burning furnaces at temperatures controlled by the glassmaker's experience and judgment. Modern glass is fired in gas or electric furnaces with precise temperature control. But precise control doesn't mean better results. The temperature variations in medieval furnaces might have contributed to the glass's properties in ways we don't understand. The loss of this knowledge means that restoring medieval windows damaged by war, pollution, or age is problematic. Conservators can't make replacement glass that perfectly matches the original. When cathedral windows need repair, the new glass is noticeably different from the 800-year-old glass it replaces. The repairs are visible as patches of slightly different color that don't blend with the original. We can make stained glass. We can make beautiful colored glass using modern techniques. Modern stained glass artists create stunning works in contemporary styles, but we cannot make glass that looks exactly like 13th century cathedral glass, because the specific techniques used to create those particular colors have been lost. Silphium. Silphium was a plant that grew in ancient Libya, prized throughout the Greek and Roman world as a contraceptive, seasoning, and medicine. It was so valuable that it appeared on Cyrenaic coins and was worth its weight in silver, making it one of the most expensive substances in the ancient world. Ancient sources describe it as extremely effective for birth control and widely used throughout the Mediterranean by women who wanted to control their fertility. The plant grew wild in a narrow coastal region near the Greek colony of Cyrene in modern Libya. Ancient sources describe attempts to cultivate it elsewhere, all of which failed. Silphium apparently could only grow in its native habitat and resisted transplantation. This made it inherently limited in supply. The amount available depended on what grew wild in one region. The Romans harvested Silphium from the wild, and as the Roman Empire expanded and demand increased, the plant was overharvested. Pliny the Elder, writing in the 1st century AD, noted that Silphium had become extremely rare. The last known Silphium stalk was reportedly given to Emperor Nero around 50 or 60 AD as a curiosity. After that, references to Silphium in historical sources cease. The plant went extinct. We know what Silphium looked like from descriptions and images on coins. It was a tall plant with thick roots, fennel-like leaves, and yellow flowers. We know what it was used for from extensive historical sources: contraceptive, treatment for various ailments, seasoning for food, and perfume. But we don't know exactly what plant it was. No specimens survive, and botanical descriptions from ancient sources aren't detailed enough for modern identification. Multiple modern plants have been proposed as possibly being Silphium, or related to it, but none match the ancient descriptions completely. The most likely candidate is a species of giant fennel, Ferula, possibly Ferula tingitana, or a now extinct variety. Some researchers think it was a now extinct variety of Ferula that was unique to the Cyrene region. Others believe it might still exist somewhere but hasn't been identified, because we don't know exactly what we're looking for. The problem is that ancient descriptions weren't botanical in the modern sense. They described uses, value, and general appearance, not detailed botanical features like leaf arrangement, flower structure, or reproductive characteristics that would allow modern botanical identification. Ancient writers assumed readers knew what Silphium was and didn't need detailed descriptions. Even if we identified the plant, we probably couldn't use it the way Romans did. The knowledge of how to prepare and use Silphium was lost along with the plant. Ancient sources mention that it was used in various forms, as resin extracted from the stem, leaves, roots, and seeds, but don't give detailed preparation instructions. They don't specify dosages, preparation methods, or exactly how the contraceptive effect was achieved. The loss of Silphium is particularly significant because it was apparently an effective contraceptive at a time when birth control was desperately needed. Roman women had few options for controlling fertility. An effective plant-based contraceptive that was widely available and affordable could have changed demographic patterns and given women more control over their lives. Instead, it was harvested to extinction within a few centuries of becoming widely used. Modern research on the contraceptive properties of Ferula species has found that some do have anti-fertility effects in animal studies, supporting the possibility that Silphium was real and effective. But without knowing the exact species and preparation methods, we can't recreate the contraceptive Romans used. We cannot make Silphium or recreate its properties because we don't even know for certain what plant it was. The technology of using this plant for medicine and contraception has been lost so completely that we're not even sure what we lost. We have descriptions of what it did, but not the knowledge of what it was or how to use it. Tyrian Purple Dye. Tyrian purple, also known as royal purple, was the most prestigious dye in the ancient world. It was produced from the mucus glands of certain sea snails, Murex brandaris and Murex trunculus, and was incredibly expensive, worth more than gold by weight. A single gram of pure dye required thousands of snails. The color was reserved for royalty, nobility, and the very wealthy. Roman senators wore togas with purple stripes, and only the emperor could wear garments dyed entirely in Tyrian purple. The dye was produced throughout the Mediterranean for over 1,000 years, with major production centers in Tyre, modern Lebanon, Sidon, and other coastal cities. The process involved harvesting thousands of snails, extracting the tiny mucus glands, each snail providing only a drop of secretion, and processing them through a complex fermentation and dyeing technique that took weeks and produced a terrible smell. The exact production method was kept secret by the dye makers, who passed the knowledge through specific families and guilds. The secrecy ensured their monopoly on this valuable product. When synthetic dyes were invented in the 1800s, particularly when William Perkin synthesized Mauveine, a purple dye, in 1856, Tyrian purple production became economically unviable and stopped completely. The families who knew the exact technique died out, and the knowledge was lost. We know the basic process, extract mucus from murex snails, expose it to air and sunlight to develop the color, ferment it, use it to dye fabric. The secretion is initially yellowish but turns purple through a photochemical reaction when exposed to sunlight. But the details matter enormously. The fermentation time, temperature, additives, and dyeing technique all affect the final color. Small changes in the process produce different shades. Different ancient sources describe Tyrian purple as different colors. Some say it was red purple, like crimson. Others say it was blue purple, like violet. Still others describe it as blackish purple. This suggests either that different production methods created different colors, or that the color varied depending on the snail species used, or that Tyrian purple was actually a range of colors rather than a single shade. Modern attempts to recreate Tyrian purple have produced purple dyes from murex snails using methods based on historical descriptions and chemical analysis. But we can't verify if they match the historical color. Ancient dyed fabrics have faded over centuries of exposure to light and air. We have no authenticated color sample in pristine condition to compare against. The purples we see in ancient fabrics might be significantly lighter or different in hue than they were originally. Additionally, the murex populations have been depleted by pollution, overfishing, and habitat destruction. The snails still exist, but are much rarer than in ancient times. Large-scale production would require harvesting tens of thousands of snails per kilogram of dye. Environmentally unsustainable and economically absurd when synthetic purple dyes cost pennies per kilogram. Chemical analysis shows that Tyrian purple dye is 6,6 dibromo-indigo, a molecule that can be synthesized in laboratories. We can make chemically identical dye artificially, but chemically identical doesn't mean identical in all properties. The texture, dyeing properties, and exact shade might differ between synthetic dibromo-indigo and naturally produced Tyrian purple due to impurities and processing differences. Even if we wanted to recreate Tyrian purple dye production exactly as the ancients did it, we probably couldn't. The precise technique is lost, and the environmental conditions that allowed the ancient dye industry to function, abundant snails, no environmental regulations, cheap labor, no competition from synthetic alternatives, no longer exist. We can make purple dye easily now. Synthetic dyes are cheap and available in any shade, but we cannot make Tyrian purple exactly the way the Romans made it because the exact technique has been lost, and the industrial infrastructure to support it no longer exists. Greek automata. Ancient Greek engineers built sophisticated automata, mechanical devices that moved and performed actions automatically. Descriptions survive of mechanical birds that sang, statues that poured wine, doors that opened automatically when fires were lit on altars, and mechanical theaters that performed plays through complex systems of gears, weights, and hydraulics. The most detailed descriptions come from Hero of Alexandria's writings from the 1st century AD. He described dozens of automata and pneumatic devices, providing some construction details. But his descriptions aren't complete instruction manuals. They assume the reader has basic knowledge of mechanics and metalworking that we no longer have context for. Some of Hero's simpler devices have been recreated successfully based on his descriptions, basic hydraulic mechanisms and pneumatic toys. But the more complex automata remain difficult or impossible to replicate based on surviving texts alone. The descriptions include ambiguous terms, references to techniques not explained in the text, and gaps where knowledge was assumed. Modern attempts to build Greek automata often require guessing about mechanisms that aren't fully described. Researchers make educated guesses based on engineering principles, but we can't verify if the reconstructions match how the originals actually worked. The knowledge of how to build these devices was lost gradually as the technology became less fashionable, and the craftsmen who made them died without passing on their complete knowledge. By the medieval period, descriptions of ancient automata were regarded as legends or exaggerations, rather than actual historical devices. When mechanical automata appeared again in medieval and Renaissance Europe, they were essentially reinvented from scratch. Clockwork mechanisms and automata from the 1500s or 1700s used different techniques than ancient Greek devices. The continuous tradition of automata making had been broken. We know ancient Greek automata existed. We have the descriptions, and some archaeological finds of mechanical parts support the accounts. But we cannot build them exactly as the Greeks did because the complete knowledge of their construction techniques has been lost. 10 technologies humanity created successfully, then forgot how to make. Roman concrete that lasts 2,000 years while ours crumbles in decades. Damascus steel with sharpness and flexibility we can't replicate. Stradivarius violins with sound quality modern instruments can't match. Greek fire that burned on water. Formula lost completely. The Saturn V rocket that sent people to the moon. We can't build another. The Antikythera Mechanism, mechanical sophistication that appeared and vanished. Medieval stained glass colors we can't reproduce. Silphium, a contraceptive plant harvested to extinction. Tyrian Purple Dye, exact production method lost. Greek automata, complex mechanical devices we can't fully recreate. These aren't myths. These are documented technologies with physical evidence. The concrete structures still stand. Damascus steel blades exist in museums. Stradivarius violins are played in concerts. Greek fire's effectiveness is recorded in multiple historical sources. Saturn V rockets are on display. The Antikythera mechanism has been recovered and studied. Medieval glass is in cathedral windows. Ancient coins show Silphium. Purple-dyed Roman fabrics survive. Descriptions of automata were written by engineers who built them. We know these technologies existed and worked. We just don't know exactly how to make them anymore. The knowledge was lost through different mechanisms. Sometimes intentional secrecy. Greek fire's formula was guarded so carefully it died with the last people who knew it. Sometimes economic change. Tyrian purple production stopped when cheaper synthetic dyes appeared. Sometimes environmental silphium was harvested to extinction. Often, knowledge wasn't written down completely. Master craftsmen taught apprentices through demonstration. When traditions broke, when the last master died, without passing on complete knowledge, it was gone. The Saturn V case shows this happens even recently with modern documentation. Blueprints aren't enough. Manufacturing complex systems requires tacit knowledge in workers' heads, in custom tools, in practice techniques. When that knowledge isn't explicitly preserved and people retire or die, it disappears. We can make things different. Modern rockets are more cost-effective than Saturn V. Synthetic dyes cheaper than Tyrian purple. But different isn't always better in every way. Roman concrete is genuinely superior for longevity. Damascus steel had properties modern steel doesn't have. Stradivarius violins sound better than modern instruments. This challenges linear technological progress. We don't always build on what came before. Sometimes we lose knowledge and work around gaps. Sometimes we replace superior technology with inferior alternatives because they're cheaper or more convenient. We can analyze Roman concrete molecularly, but can't make it economically. We explain Damascus steel's nanostructures, but can't forge it. We measure Stradivarius violins precisely, but can't match their sound. Understanding what something is doesn't mean understanding how to make it. 10 technologies we had and lost. 10 reminders that progress isn't always forward, that knowledge is fragile, and that sometimes humanity loses capabilities our ancestors possessed.